Hi, everybody. My name is Alexey, and welcome to my talk, Deep Learning in Scala 3 from Scratch. So I'm a solution architect working at EPAM. I'm also functional programming. I'm working with Scala for quite a while, also with Java. Sometimes talk at the Rhein-Main Scala meetup in Germany, and also like different stuff like music, guitars, and astronomy. So the talk for today, and the goal of this talk is basically to get an idea of what is a deep learning and what is deep neural network and what's the computation behind that. So we're also going to be using Scala 3 features in the implementation. And one kind of side goal from my side is to inspire you to someone from the community to write a good long-standing Scala library for deep learning, or maybe to join the forces. So you would be also interesting to start such a journey. So, and the agenda is do some intro into deep learning. So you don't necessarily need to know what it is, but some basic knowledge would help. Then also look at what is actually tensors. And then we'll implement the network in Scala, and we will perform look at the results of the training and tests and some visualization for this process. Okay, let's get started. So before we starting the implementation, we really need a little bit to understand what's behind deep learning and what it's based on. So deep learning is a part of the machine learning in general, and it's inspired by the biological neuron model, which is sits in our brain. What's the brain constructed of? One of the pieces, right? And that was inspiration to build the kind of deep feed-forward neural networks, and the model of the neuron was borrowed to build the kind of mathematical model, and then that whole set of algorithms was called the neural networks. So what do we have here in the neural model and the artificial neural model on the right-hand side? So there is something like inputs and outputs that you can see in biological neural model that have like you see the inputs like x1 and xn, and then outputs is y. And here, different things like cell body and the axon. So this is something that was used to it was inspiration to build a mathematical model, and then try to, then use this algorithm to be able to learn the weights and biases to then produce some useful outputs. So what's the artificial neural model? If we look at just one kind of perceptron model, which has one neuron in it, at several inputs. So we also have different variables, like X independent variables. We also have on another side, we have Y, which is the output, which our model would predict. And inside, or in the middle, we have kind of one neuron, which represents with this summing junction and some application of the output of this summing junction to apply some nonlinear activation function F. So every connection or arrow input has some letter, right? This X, W, Z, Y. So during the presentation, try to remember these letters. They are kind of taken from the literature, from the theory, and that will be used also in the Scala code. So the important here in the artificial neural model that it has some parameters which are called weights and biases, which are basically the model state. So I will be switching between this theory and into the programming kind of techniques of theory. So the model state is something that we're going to be modeling with Scala and mutating during the training, and we'll try some parameters to then will be stored in our model that we can use it then to predict some different things based on this model. So inputs are individual independent variables. This could be some kind of what machine learning engineers call, or data scientists, features. And the outputs is something, some dependent variable that we want to predict. For example, the price for housing in specific area. Or one of the use cases we're going to be using today is the churn modeling, like whether the customer leaves the company or not, based on different attributes or features that this X variable represents. There are some formulas inside. Also, you can see that inputs are kind of connected with the summing junction with the neuron. They have these weights on the edges, and there's the formula, this summing junction, where we multiply the x variable by its weight, and then we sum up this some bias variable, which is also changing. This is how the model, how the inspiration was taken from the biological neuron model. So deep neural network is the network that has multiple layers inside. These layers inside are called hidden layers. And that's the whole basically trick of the neural networks, that they have some nested layers which are able to learn, and they are useful. And that was kind of the big discovery back then, when the whole move was started with the neural networks, and then later kind of rebranded to the deep learning. And you can see that these neural networks can be such big. And for example, this is just like one dot here over here, and if we like zoom in, then this kind of network, this smaller representation, just for only one neuron. So you can see that this yellow one is on zoom in picture here, and then you have different edges coming into this neuron, and you need to have this formula or calculation, and then to output some value, which will be the input for the next layer. So by the end of the day, you kind of have this neural network as a function, so which we get used to in Scala, where we put some input value and we have kind of deterministically some output value from this network. So this just is the big function, and as you will see by the end of the presentation. So we said that there is an input layer, there are several hidden layers, and there is one output layer, which may predict some value, usually from between 0 and 1, but then transfer the map to some domain. Also, it's worth to say dense layers. Here we present this example is a network consists of the dense layers, so fully connected layers. The other types of networks may have non-fully connected layers. We will skip them for today. So I probably should have been saying that, the first part will be quite theoretical, then we will switch to the Scala implementation. And this theory is quite, I would say, maybe not so heavy, but kind of big. So the entire kind of encoding implementation or programming those networks is not that complex. So it's more theory than actually programming here. So let's look at the deep feed-forward network closer. So what does it do, and what the algorithm actually is? We have this network which we will feed data into from the left-hand side, and we will have output on the right-hand side, and then we will do that during several iterations, and this process is called training. So we train this model until we are satisfied with the results. We can be satisfied once we compare the results with some kind of expected results. So how does it do this? How do we do this with neural network? We have some input data which we feed into this graph, right? So this network. We apply those calculations, those formulas on every neuron, and eventually that outputs our y variable, or some prediction. This kind of training on this kind of algorithm, it's a supervised machine learning approach, a method where you have also expected results which you can compare with. So you kind of train this network by yourself, so you're kind of supervisor. So that helps us to, on the output, to compare the prediction with the training data y, the expected y. And the difference is something which is called like error or delta. Then it's used then to propagate the feedback to this algorithm and improve its internal state. The kind of second part of this, once we've got the delta or difference between the predicted and expected, we use a gradient descent algorithm, and using that, we then adjust the weights and biases and repeat the whole loop again. Oh yeah, that's also worth to say that first time when we start, the all weights and biases, these W's, and also there are the B variable letters, and I skipped them on this picture, but you've seen them before, just for not overwhelm too much. But they're also kind of on every neuron, there's a kind of B variable or parameter. First time when you initialize them randomly, there's also different techniques how to initialize them properly based on the statistics of the input data and other stuff. And also this error or delta then is kind of used or based on the idea of loss and cost function, which we need to minimize. So we want to minimize the cost. This is our objective function here. Loss curve. So when we measure this error, so we use also a cost function or cost function. This is synonymous in theory, deep learning theory. Over the time when we run our training over different many iterations, which are called epochs, we should have seen to see that such kind of flow or the learning or loss curve should drop down. That means good, that our algorithm is learning something useful, and then we eventually will be using this model for something in real life. Loss and cost functions are chosen based on your task, on your problem. There are problems like regression and classification, which your model may output the numerical value or binary value, like 0 or 1, or if you would convert it to your domain, it's something like a yes or no question. Classification, which could be you have multiple classes and you want to predict a single label on your data. Or you have multiple labels. So typical example of multiple classes, multiple labels is in computer vision, you have a picture where I have 10 different classes like autos, pedestrians, roads, traffic lights, and each picture can have many of them. That's kind of multiple labels, multiple classes. In our case, we're going to be using the loss functions, which we will look at the example later, would be a classification, and it would be binary loss function, which we will predict kind of yes/no question. That's the formal and mathematical representation where we have this y, the expected output, and the y hat is kind of actual prediction. So by this moment, you might ask yourself how to fit one or many data records into the network. So having n layers with multiple neurons each. So we may have a network. So let's take an example which has 12 inputs and then 2 hidden layers, which every layer has 6 neurons each and 1 output of this network. So let's look at the example with such a network. So let's take n to 12, right? So this is the schematic visualization of such network, which is a bit simplified. So I haven't drawn all the neurons, and you may see that here the x1, xn, it's like 12 inputs here. Same here from 1 to 6. So imagine that there are 4 more in between here and here. And there are some also additional new terminology that I will clarify later, like this ReLU and sigmoid, which are basically activation functions. So in order to fit into such a neural network, we actually rely on the linear algebra, and specifically on the matrix multiplication. That's the key mechanism with the neural networks, and the whole calculation mainly based on them. So imagine we have x, which is the input, and usually when we train such a network, we don't really feed only one data sample. We may feed a batch of them. So in this example, we took 16 data samples during the training, and our input, there are 12 input variables. So we will have basically a matrix, which will be 16 to 12. And the whole fit process is, if we reuse that earlier sum injunction formula, you will see the sum of the inputs multiplied by weight plus biases, and rewrite this into the matrix multiplication. That will look like this. So we'll have this matrix of X, and also we'll have the second operand, the weights, which would be dependent. The size of the weights or matrix or shape will be dependent on the X shape, which in our case, that would be 12 to 6. So 12 is the number of the inputs right here, and the 6 columns is how many neurons we've got in the hidden layer. Plus biases. For every neuron, we have one bias variable. So we have 6 of them. So it's going to be like a matrix with 1 column here. So that's the one layer calculation here. So once we've got this dot product plus bias column matrix, we've got this activation, which is called that in literature. And then we need to apply nonlinear activation function, which are also chosen based on your task or based on the latest discoveries of this activation function. So we apply some activation function, which I will show you later what it is. And we've got the neuron activity, which is in literature called A. So that's one full calculation from one layer from X to this second layer. Then this A will be the input to the next layer, and so on and so forth. So many layers, so many such typical calculations. Yeah, that's what I was saying, that here is a dot product operation, and between the result of this operation and the biases, we use a kind of broadcasting, or like we sum up this column to every, so this B1 will be added to every element of the first row, and so on and so forth. And if we would feed only one record or one data sample, that would be 1 to 12 matrix, and output will be 1 to 6. Activation functions allow us to basically learn parameters. So the whole idea that they're kind of non-linear activation functions, they kind of squish the input value into some range of value. For example, sigmoid, kind of traditional non-linear activation function, is squishing the input to be between the 0 and 1 non-inclusive. And the more kind of modern activation function which is used today usually is the ReLU or leaky ReLU. So you can see there are formulas, like quite simple ones, which, for example, ReLU just setting to 0 all negative numbers and just return the X if it's not non-zero or greater than. So it's important to say that so it should be kind of non-linear activation function. Otherwise, if every activation function or layer will be a linear, so mathematically we will then prove that the whole composition of them will be just linear function, which will actually not learn anything, so it will be kind of useless. Yeah, so what's important also to mention that when we apply this calculation for one layer or for the rest of the layers, we need to follow the linear algebra rules. For example, for matrix multiplications, where we have to have all kind of number of columns equals the number of rows between the operands. So that is why this X is transposed here. Now we come to the implementation in Scala. So we've got this dot product, right? So how we would implement? So that would be just a matrix multiplication, so matmul function that takes two arrays, array of arrays, so matrices, and just we're gonna use a naive algorithm of the matrix multiplication. There are more advanced versions of it and more computationally effective if you would use something like a GPU with some frameworks. But yeah, what's doing is just multiplies row by column and then summing the results, and then we have back the another matrix which would be a bit different shape than these two operands, but it will have some dependencies to that. One of the rules that we need to follow basically to verify the A and B is that the number of columns in the first matrix should be equal to the number of the rows in the second one. So that's the comment from the linear algebra itself. That's how we do calculation to get the Z before we apply activation function. Actually, we will after this calculation, we apply biases and then activation function. One of the Scala 3 feature is the new implicits or the new using keyword. which we will use here. So we abstracted away the precision of the numbers, which we just require a numeric type class. And then we say, okay, that's as long as the T has numeric type class, we are good to multiply numbers here, right, and summarize them. So generic multidimensional array. That's another topic that we will talk. So you notice that all these operands may have different shapes. So we have X, weight, bias, Z, A, Y, and Y hat. They can be scalar, just a vector, or matrix, a cube. So we want to have some abstraction that would tolerate them or that would treat them in the same way. So such abstraction exists. So it's called in computer science tensor. It's not necessarily the same thing as in physics the tensor, but just like take it as a granted. So the tensor is something like an n-dimensional array of data. You might have heard this word from the popular framework TensorFlow. So how does it help? We can basically program such abstraction, maybe call it tensor. Yeah, we will call it tensor. But there's some terminology about that. So if you deal with the kind of matrix with just a single value, or like a vector, just a single value, that is called tensor rank 0, and that's also known as scalar. Then the vector is the rank 1, which is also known as vector. The matrix is rank 2 tensor, then rank 3 is some kind of different tensor. So it's a kind of, you can call it a cube, right? The rank 3 and rank 4 is something like a array of a cubes. So that's what we're going to be using. So how can we model that in Scala? So we will follow quite simple design with this tensor. So we're not going to support any dimensions. We'll just support a couple of dimensions, so a couple of ranks. So I decided to follow it a bit kind of straightforward way. So we're going to have filtrate tensor with the two abstract methods, length and shape. And tensor 0D, or like a zero-dimension tensor or rank 0 tensor, would have just one point, this data of T, where the shape would be the length, and the length is 1. So quite simple. The vector is the wrapper around the array, which has the shape, which would be just the length of this vector, and length is just the first dimension of this array. So tensor 1D is it's anyways only one kind of array, but you see in the matrix we have a little bit more different implementation for shape and length. When length probably is going to be everywhere the same, it's just the list of R and C, so just the two values. And then we need to define a set of operations, basically a lot of them, to make the computations of deep ferret networks convenient. For that, we're going to be using Scala 3 features extension, and we'll implement a bunch of extension methods. This is just the main ones that I put on the slides, or just kind of a list of them. But in the project that I have on GitHub, it's quite a lot of them, which I tried to implement that and to see if it's going to be working or not. So that I started from the project before and then kind of putting this onto the slide. So here what we have is several important operations like dot product, that's kind of corner store operation, then element-wise multiplication, which is in literature called Hadamard product, or we call it just multiply, and different things like minus operation or addition and sum. And all of this extension method, they delegate the calculation to some class or object, which there will be real implementation, this tensor ops. So they are not so important. So you already seen how the matrix multiplication can be done in a naively way. So that's encapsulated here in the small methods. Yeah, that's what I mentioned, that we used the extension from Scala 3. So let's look at the data set and the example that we're going to be using to implement a real training algorithm as a library, and then we'll use this data set. So we're going to be modeling today the Churn Modeling, where the question is whether the customer exits the bank or not. So imagine we are some corporation, a bank, we want to predict based on some data that we have of our customers, whether they're going to be leaving us soon or not. So that will be a problem or task of binary classification. And the answer would be yes or no. We're going to have such input of data where we will have like raw data in a CSV file. And here you see that input features as X would be something like credit score, geography, gender, age, has credit card or not, is active member, and different things. So it's around 10 features from the raw data. And the answer would be this column, which could be called exited, like exited yes or no. So what do we have as input data? You may see this is this data sample here, a couple of rows. How does it look like? So we can't really feed this data into the neural network. We need a little bit to transform it in code and scale. So how do we do that? So the reason for that, just because neural network won't work and won't understand the categorical data, for example. We have a couple of columns for that. So this is the geography and gender. We have different countries in geography and gender. We have two genders here in this data set, female, male. And one of the typical or usual approach how people approach this task for preparation of data, they use kind of encoding algorithms where for the geography with more than two kind of categories, we use one popular algorithm called one-hot encoding, where you say if so you represent your whole feature as a vector, and you set 1 into the place where this value is basically positioned. For example, we have these 3 countries here, I think, France, Germany, and Spain. And we set here that this 1 means that this is the, I think, France, for example, right? And this one here, this means this is this Spain, right? This is just a vector of zeros, and in some position you have 1, which is something like a flag, and every position is set for specific country. So this is what one-hot encoding is doing. So basically, it transforms this categorical string data into the multiple columns, so it explodes the data set and add more features to it, kind of more columns, and that will be also numeric, like 0 and 1s. For gender, similar thing, but we use just a label encoding algorithm where we say for female 0, for male 1. So that's how we transform the input raw data into the final input data for the neural network. In the result, we've got more features. I think there's going to be 12 right now. So that's where that 12 input is coming from. Also, we do some data scaling for neural network to work better. So that's another technique that is used. So I must say that deep learning is full of that tricks and tips to apply different pre-calculations and different things to make whole training be more efficient. And it's really a lot of techniques and small algorithms, but the basic one is this kind of feed forward and backward and gradient descent. So for scaling, we calculate the mean and standard deviation for every column, and then we scale or apply this information to every value of this column. This is the formula, what we do with the input data. So eventually our input data became like this. So you have here like really small numbers or big numbers here, but that's fine. So we're almost, I think at this point, we are ready to feed this data into the training. That's a little bit of code, how you could model this encoding algorithm in Scala. For example, label encoder as case class with the feed and transform method, same for one-hot encoder, where you give to the feed samples again in the tensor abstraction. So you have kind of label encoder which already knows how to encode your data. And then you call the one more method transform, where you give the actual data and then it returns you back with this encoded data or scaled data. So these algorithms are not really complex one. So it took me like half an hour to implement them in Scala, and they're quite small ones. So you don't necessarily need to program a lot of things. Of course, once you're going to be more abstract and more robust and add more features, that's when the code is growing. But the whole, this artificial neural networks deep feed forward, kind of generic implementation with this encoding. Doesn't really take that much code, and I will share a link to the GitHub project where you can see that's not that really difficult. What's actually will be difficult, and then to provide lots of tooling and ecosystem to developers to be more effective and run all this stuff with GPU and so on and so forth. So that's kind of a side note here. So now we're gonna load in this data from CSV file into the memory and then feed this data into the training network. So I developed some kind of text loader basic class that's just using the path API from Java to load the file into a memory. Eventually, this data will be put into the tensor. So we have CSV kind of data frame. So it will be a matrix. So it will be tensor 2D. And what we have here is we skip some of the columns from the CSV file, like customer ID or something else that basically not needed for the machine learning model. So we don't really benefit from those columns. This is how we do here with this 3 and -1, where we take all columns starting from the number 3 index and skipping the last one, this -1. So someone who are familiar with the NumPy or different libraries from Python might know this notation, like this -1 thing. So we take this data from the input CSV file, and then we apply these encoders that I mentioned before. So just a bunch of code here, but you don't necessarily need to understand in full details. So we construct these encoders as the pure functions in Scala. And yeah, we compose encoders and transformers into one, like prepare data, which takes the tensor 2D and gives back tensor 2D of type T, and that would be floats. So once we take this data and we feed into the prepare data function, that will be our X finally. And CSV file has 10,000 samples. Also, we take the last column, which is Y, which has already expected value. So it's supervised machine learning, and we already have data with the already available or known predicted values of Y. So we take this Y as a separate tensor. And additionally, before starting the training, we split the whole data into 2 data sets, training and test. So we're going to be training our model on the train data set, but never showing the test data samples, and we'll evaluate its accuracy or the efficiency on the test training set. So we split this to 80 to 20% with this fancy method split. So most of the things which you see like a dot something method is an extension method in Scala implemented on this tensor trait. So 0.2 means 20% for the test here, and 80% will be left for the training data. Yeah, eventually we'll have 8,000 training data samples and 2,000 test data samples. So let's implement the network. How we can design this graph? We have some abstractions here, right? So I think typically Scala developer approaching this, trying to model using some domain-driven design, something like that, to map the entities into the case classes or traits. So I decided to follow this idea and just be straightforward, just to maybe explain this to other people easily. So what we have here, we have a layer with contains weights tensor and bias tensor, and it has some activation function, and also number of units. This is how many neurons it may have. Activation function itself is just a trait which has apply method that takes tensor, return tensor, and also derivative. Derivative is another kind of dual function to the activation function, which is used for backward propagation later. And also have a loss function, which is again like takes some tensors and returns a value, just one single value. So here it returns the loss value based on the actual and predicted Y variable. So they are tensor type, but this all will be Y and Y hat from here. This will be a kind of delta between the output and the expected value. Okay, so the model itself can have train and layers and predicted method. We will be using train to train the network, layers that will be actually the state, and predict that will be used later once the model is trained. And eventually we'll have the case class sequential, which is something like a type of the model, which potentially could be other different models, which can would have this loss function, different parameters to deep learning network, and this layer stack, which we will be populating. Loss function, learning rate, batch size is to be specified by user, by machine learning engineer, data science, who's going to be training that. And learning rate and batch size also called hyperparameters. That's sometimes you may hear that when people discussing the machine learning algorithms. What's actually a layer config here, or what's the dense, right? So I've come up with this kind of builder pattern approach to create a sequential class first, provide static parameters, and then user could call add method to add more layers, how many is needed. And dense is kind of layer config that contains this activation function and number of units, like how many neurons we want to have at each layer. The kind of final API looks like this. Someone who is familiar with the Keras library, which is working on top of the TensorFlow, may recognize this kind of API. The batch size means that we update base weights and biases on every 64 training records. So let's a bit trace how we construct this dynamically, the whole network, by having this API. So if inputs equal to 12, so we have this 12x independent variables, then we must have the next hidden layer with 12 rows. So that's because of linear algebra. So this kind of connection you will see here with the colors that I made. Then the second hidden layer must have the number of rows equal to the number of columns in the previous hidden layer. That's the connection we need to follow. So having this kind of algorithm, you see that the kind of last digit on this shape equal to the first digit on the shape of the next layer, we can construct this by not specifying in advance how many inputs we have. So that's the trick I used in this add layer. So it's kind of fancy layer that creates a closure, and based on the inputs, it runs the existing closure as the current layer, building a new layer, and adding to the current layers, and build up this closure. And eventually, yeah, this will be just run for inputs, for int, and you will have this kind of stack of layers properly constructed without kind of mistake that user could potentially make if they would specify manually this 12 to 6, 6 to 6, 6 to 1. The training algorithm looks like this. So we have two tensors, x and y. We have layers, which are randomly initialized at the very beginning. We feed them through the activation for all layers. We have the history of activations. And the last cell of activation, we get the predicted value. We compute the delta. We have the error. So this is just the sequential steps here. And then once we have the error, we can update the weights, and we repeat that for a number of epochs, for example, 100 epochs. And if everything is correctly implemented, then we will see this loss curve is falling down. So this is the input variables, that's internal state, and that's basically the most important thing that you need to remember from this code presentation. So how the training, so perhaps that the last few slides would be the most kind of heavy code slides, which you need to a bit focus if you want to understand this algorithm. Yeah, but only a couple of slides, not more, so we're almost finished. So for training, we have these two input parameters like x and y tensor and number of epochs. And we have the first loop here, which is implemented through the fold left. So we are folding through just on index range from 1 to number of epochs, for example, 100. And we're using some batch of input samples to calculate the loss and update the weight. So every epoch, we calculate the loss and update the weights. Before that, we split the x and y into the batches. There's additional fancy functions like dot batches. This is, again, those extension methods for a tensor trait or tensor 0D trait, something like that. And we initialize layers using that closure that I shown before based on the shape of the inputs. Once we have this all constructed variables, we feed them into this fold left loop, and internally we call train epoch. So what's going on further? In the nested loop of train epoch, we have second loop, and that second loop is actually iterating over the batches. And here we have the first time kind of update the weights. So we calculate here, we activate, we take the X batch, we go through the activate function, we have activations, we have the actual Y. This is the 2D tensors, basically the 16, for example, Y's expected variables and 16 predicted variables. If it's a batch training, we have a difference between them. So this is the minus defined for a tensor trait. So this is two variables of type tensor. This is not on numbers. And then we calculate the loss. So activate, go through all layers. So what's happening in activation, on activate function? We have the input tensor and we have the layers. We go through each layer, so again, folding left, and we kind of trace or create activation history. You see the return type is a list of activation, and here it's even like mathematical description. If you would ever read the deep learning theory, you will see this formula. We also have seen that in the very beginning of the presentation, that we multiply x by weight plus bias, and then apply some f function, which is activation function, and then we get this A. So that's like exactly just mathematics here. So we're folding over each layer. Then we return the list of activations. Yeah, also, you notice this pattern that current activity is the next layer input, right? So once we get this A output of one of the layers, we feed it and use it as X here on the next layer, right? So this A becomes next X once the folding left progresses through one iteration to the next one. So that's kind of recursive. Activation case class, just keeping track, encapsulating this X input layer, input tensor layer activation. So we kind of keep history before the apply an activation function. We keep also that value. And then once I apply the activation function, we keep the activity of this A variable. So I try to keep all these letters and the naming convention that is coming from the literature and also in the code, so that if you would come back to that, so you will kind of start to map what you would learn in the theory, instead of just going with the full names of the something like activation or something like that. That would be much more code here. Yeah, this is how we, if we come back and compare this visual representation of the neuron calculation, this is where these variables are sitting on which age. Once we've got this activation, we are ready to perform update the weights. So we need to update the weights because we have initialized them randomly. If we just do anything, we will run algorithm for 100 epochs. Nothing will change. We will just hit the CPU of the server or laptop. So we need to find better ways to have a smaller error. So we call some optimizer update weights, which returns a new list of layers, which we use again on the on another epoch. So it's just a iterative algorithm. So now we're coming back to optimizers. And optimizers is this kind of final part of the deep learning or gradient-based machine learning approach. Optimizer only has one method, update weights. So it's represented as an optimizer trait. And for the kind of type stub, if we define one, then it would do nothing. So it just takes the layers and other parameters and return the same layers. So if we would use such stub optimizer, and yeah, the givens are from the Scala 3, then we would train such network. Then what we will get if we represent the statistics out of that is kind of useless results, because our training accuracy doesn't change. So it's at 35% of right answers, and learning loss is basically larger than double dot max. So it's so big value, and it's also never changing. So it's just a useless kind of algorithm. But we need to really make something useful inside this update weights. So what can we do? One of the popular taste or kind of flavor of this gradient descent is the stochastic gradient descent, or also batch gradient descent algorithm. So I decided to call this standard gradient descent, standard GD. And what does it look like? So that's probably the most complex part of this algorithm. So I promise that's the last part, last slide with the complex code here. But if you would trace this code, that's exactly what's if you would look at literature or scientific paper on deep learning, you will see this kind of calculation. So we are going back. So that's why it's called backpropagation. And we use fold right here. So that's a useful method that we go through each layer and we calculate new bias and weight, and we construct new layer out of the new values, and we add this to the list of layers. So what do we do inside? We use some, probably skip this full mathematical explanation here, but what do we use is the weights and biases and this delta that we calculated on the output of the feed forward way. And then we propagate also that recursively back. So we update weights of one layer based on the updates of the previous layer. But we go from the back. That's why it's called backpropagation. So why it's called gradient descent, it also requires a bit of time and explanation. So I think we don't have time for that, but I encourage you to also to have a look what's in the mathematics or the idea behind this gradient descent means. But one of the way to encode that, it's basically on this slide. So we go backward with a fold right. And if we run the training process, then we will finally see that the metrics are improving. So we have better accuracy with the 86% right answers, and loss is falling down. If we test our use case with the churn modeling and we apply those test tensors that were left at the very beginning, we will see also good accuracy with 82% of right answers. And some just single tests for one example, just for the sake of fun to see what's going on. If we just apply this data, will customer with such data exit or not? So it predicted false means doesn't exit. And the funny thing is, how does predict method calculate the target value? We have this predict method called here. So it's very simple. You will just see. So we have this sequential model which has predict method. And it's very simple because what it doesn't do is just feed forward calculation, and the last activity is basically prediction. So that's the last element of the list collection, and this returns the activation case class, and then we have this A variable. So that's how the predict is working actually. And that's it. Thank you for watching, and I hope you like it. And I'm looking forward to your questions.
Hi, Alexey. Thank you so much for your talk today. We do have a question, and let's put it up on screen. Just 1 second here. Sorry.
Mm-hmm. Okay, yeah, I mentioned the APIs similar.
Yeah, you mentioned the library that is on top of the TensorFlow with an API similar to the one you showed. Is this a Scala library?
That one that I inspired kind of my API from is the Python library. It's called Keras. I've seen several Scala implementation kind of following this idea that you kind of construct the model and then you have different builder methods. But I think none of those libraries are yet mature or production kind of ready libraries, unfortunately. Yeah. So answer no, it was Python library.
Yeah. We have one more question that I'd like to ask you while we still have a couple minutes here.
Mm-hmm.
And just 1 second. My apologies for the delay. what do you think are the most important missing pieces that are currently preventing people
Good question.
from using
I think
Scala for deep
tooling
learning?
and the support of the GPU, because they are resource intensive. If you train them for computer vision tasks, you need to be very effective with your hardware. So state of the art is to use the GPU or TPU. And we boil down to JVM support. So I think in some version of JDK, we're going to have the vector API, which would allow us to use SIMD, the CPU approach to parallelize the multiplication of numbers. But perhaps, yeah, the GPU support, it exists in some libraries here and there, but I haven't seen them to be like mature enough to be used in production. I have some links in my slides which I can share, and there you can have more inspirations or maybe questions if you want to learn more about the application of Scala to such tasks.
I think that would be fantastic. I'd love to connect you. Attendees can get those slides.